Hi. In this video we will discuss various performance metric for our implementation. So this is called a confusion matrix, where we will have an actual label for the class and the predicted label for the class. So assume that we have some positive samples and negative samples. So this could be any class, maybe like cancer is present, cancer is not present. Rain will occur, rain will not occur. Maybe a particular country will win the match, will not win the match. So these are the two outcomes, positive and negative. Let's call it as a positive and negative. This could be any value. Maybe heart disease is there, heart disease is not there. And cancer, tumor is present, tumor is not present, like that. And this is the predicted output. So we will have some samples whose actual class label is known, whether it's a positive or negative. And after our model training and testing, we will have some predicted value for that particular sample has been classified as a positive or negative. So based on that, we will have four values. If our actual sample is positive and if it is predicted as a positive, then that sample is called true positive. That case is called true positive. If our actual sample is positive, but if it is predicted as a negative, then it is called false negative, because it was positive originally but classified or misclassified as a negative by the model, and that's why we'll call it as a false negative. Similarly, if our sample is negative, actual class label is negative, but if it is predicted as a positive, we will call it as a false positive, because classified as a positive but it's not positive, it was originally negative, so we will call it as a false positive. And if our actual class label is negative and if it is classified as a negative, then we will call it as a true negative, because it was negative and it is classified as a negative. So this is the confusion matrix. Based on this, we can have many different evaluation parameters. The first one is precision. So precision is basically percentage of correct positive predictions, and it is given by true positive upon true positive plus false positive. Similarly, we have a true positive rate, that is TPR, also known as a recall, also known as a sensitivity, and that is given by true positive divided by true positive plus false negative, and this will tell us the percentage of positively labeled instance also predicted as positive. TNR, that is true negative rate or specificity, will tell us that what amount of negative labeled instances are predicted as a negative, and that is defined as a true positive upon true negative plus false positive. Accuracy is defined by percentage of correct prediction. So diagonal values are correct predictions, true positive and true negative. Off diagonal values are false prediction. So we have true or the truly predicted labels in the numerator, true positive plus true negative, divided by total number of samples, true positive plus true negative plus false positive plus false negative. And F1 score is given as a harmonic mean of precision and recall, that is 2 into precision into recall divided by precision plus recall. So depending upon the domain and the application, we should choose different performance metric, but F1 score is considered as a balanced score. In some applications we need precision to be good, in some application we need recall to be good, sometimes we may be only depending upon accuracy, fine, but they does not reflect the perfect way of assessing the model. But F1 score is a good measure. It gives us balance between precision and recall. So let us see how we can compute those values. So I have given the example. Here we have an actual label, that is a positive and negative, here predicted. So assume that we have total 50 samples. Out of that, 17 samples were positive and actually classified as a positive. So 17 is a true positive. There were 6 samples which were positive but classified as a negative. So we will call that 6 samples as a false negative. There were 8 samples which were actually negative but classified as a positive. So false positive is 8 here. And there were 19 samples which were actually negative and predicted as a negative. So 19 is a true negative. And this is the total. 17 plus 8 is 15, 6 plus 19 is 25. And similarly 17 plus 6 is 23, 8 plus 19 is 27. Based on this confusion matrix, now we will evaluate the different parameters, like precision is true positive upon true positive plus false positive. So from this metric we can see what are the values of true positive, true negative, false positive, false negative. We will put the value in equation and we will get the final outcome. That precision for this confusion matrix is 0.68. Similarly, we can compute recall. TNR, that is the true negative rate, or also known as the specificity, accuracy, and the F1 score. To compute the F1 score, we should have first precision and recall. That is already computed in first two steps. We are just plugging the value and we are getting the F1 score to be 0.68. So this is just a demo, random samples I have considered. It is not for our experiment. This is just to explain how it works. Next is a Cohen-Kappa score. So Cohen-Kappa score is a statistical measure which computes the inter-rater reliability and intra-rater reliability. That means if suppose we have two raters, and we will take the opinion of rater 1 and rater 2, and we will see that how many times they agree or they disagree with each other, and based on that Kappa score is decided. So K is defined as a P0 minus PE divided by 1 minus PE, and if we do the mathematical simplification, we can also write it as a 1 minus P0 upon 1 minus PE, where P0 is relative observed agreement among the raters, and P0 and PE, actually this is PE. PE is the hypothetical probability of chance agreement. What that means, P0, it means P0 and PE we can consider it as a predicted and the actual class level, and we will see that how many times they are matching and how many they are not matching, and based on that we can compute the Kappa score. So Kappa score K is equal to 1 implies raters would be in complete agreement. That means the accuracy of model is 100%, and K is equal to 0 means there is no agreement at all. Means if actual value is positive, predicted will be negative, and if actual value is negative, predicted will be positive for all the samples. So in that case Kappa score will be 0. So consider these are the rater 1 and rater 2. So actually this is our actual value, actual class level, and this is our predicted class level. In that way you can consider. And equation of K we have derived from the previous slide. P0 is equal to 17 plus 19 by 50, because see P0 means the true predicted value, that is 17 and 19 are the actually predicted values. So 17 plus 19 divided by total number of elements, that is 50. So that will be 0.72. And PE, that is the probability, or we can say that is the hypothetical probability of chance agreement, and that is computed in this way. So first we need to compute the marginal probability of this, or margin of this. So this is 25, 25, 23, 27. So first we will be doing for the positive class, that is 25 divided by 50 and 23 divided by 50. So we have to go row wise, that what is the agreement on positive sample in this way and that way. So that is 25 by 50 and 23 by 50, that is the probability of positive. Similarly for negative we will be following this column and this row. So that will be 25 by 50 into 27 by 50. So that will give us 0.5 into 4.46 plus 0.5 into 0.45. So the Kappa score, so the P is 0.5. And from these two values of P0 and PE, we can compute the Kappa score, which is 0.44. We will put the value of P0 and PE in this equation, and Kappa score is 0.44. Now what is the interpretation of this score? So if score is greater than 0.8, then we can say it's almost perfect, means our model is quite good. If it is greater than 0.6 but less than 0.8, then model is having substantial classification power. Greater than 0.4 is a moderate, greater than 0.2 is a fair, greater than 0 means it's a slight, and less than 0 means no agreement. Right? So we should target to have Kappa score greater than 0.8. Next is mean squared error. So as the name suggests, mean squared error. So we are taking the mean of squared error, and error is nothing but it's a deviation of predicted value from the actual value. So yi is the actual class label of ith sample, and yi hat is the class label of predicted class label of ith sample. So this is the actual minus the predicted value. So class label may be positive, minus, negative, or maybe 1 minus 0, 0 minus 0, 1 minus 1, 0 minus 1, whatever it is. Fine. Here we have to consider the numeric value instead of the label. So this may be if this would be some number, 1 minus 1, 0 minus 1, 1 minus 0, or 1 minus 1, like that. Fine. So we are computing the deviation of this, we are taking the square, we are summing up. So that is squared error, and then we are dividing it by number of samples n. So we are taking the average or the mean of the error. That is why it is known as a mean squared error. Let us read it out. In statistics, mean squared error defines the average squared difference between the ground truth and the estimated value. So ground truth means actual value and estimated value means the predicted value, where yi is the actual value and yi hat is the measured value and n is the number of samples. Now why we are squaring this? There are two implications of squaring this. Squaring the difference will ensure that MSE is always positive. Fine? Because suppose if class label is 0 and predicted value is 1, then this number would become negative. Fine? But error cannot be negative, so we are squaring it. So that will ensure that error will be always positive number. And the second thing is that the larger the difference, the larger the square would be. So during the optimization process or updating the weight, the term which is having the larger difference would be penalized more. So that will also help during the optimization process. Here we have the example of computation of mean squared error, how we can compute. Assume that we are doing some forecasting for 4 different quarters of the year. So these are the quarter number 1, 2, 3, 4. This is the actual value. These are the actual, say for example, these are the sales of particular item 50, 60, 70, 80. And these are the forecasted values. Suppose in quarter 1 the sale would be 52 unit, in quarter 2 it would be 65, in quarter 3 it would be 65, in quarter 4 it would be 82. So actual and forecasted value we have. So we have to take yi minus yi hat square. This is actual value is called yi and forecasted value we will call it as a yi hat. So this would be 50 minus 52 whole square. So 50 minus 52 would be minus 2, but as we square it, it will become plus 4. Similarly, 60 minus 65 square would be 25, this is 25, this is 4, and when we sum up it is 58. And the equation of MSE, we know that we have to sum up the squared difference and then we have to divide it by number of elements. So right now we have 4 samples, so 58 by 4, that is 14.5 is the mean squared error for this computation. So smaller the MSE, better the algorithm or better the model. Right? If MSE is 0, it means actual and forecast value are perfectly matching. If MSE is high, that means there is a large deviation between actual and predicted values. Next is mean absolute error. So mean squared error increases the computational complexity because we have to square the number every time. In case of if you want to simplify that computation, then we can take the positive difference. Instead of squaring it, we can take like this, that MAE, mean absolute error, is given as summation of yi minus yi hat, and we will take the positive value of positive difference between them. That is the only difference in this, otherwise everything is same. And we can consider MAE as an arithmetic sum of absolute error. Okay? Absolute means positive error only. And the same example, the only difference is that now we are not squaring it, rather we just have to take the mode of that. So 50 minus 52, mode of that, the answer is minus 2, but when we take mode of that or absolute value, it will give us the plus 2. So 2552, error is 14, and then we are dividing it by n, that is 4, so mean absolute error is 3.5. So this is how we are computing MAE. Equal error rate. So equal error rate is typically used in biometric systems like a face recognition, fingerprint recognition, voice recognition. Right? In such a biometric system, normally equal error rate is being used, and it will effectively measure the efficiency of the system. So EER, that is equal error rate, is the equilibrium point for false acceptance rate and false rejections rate. So what are these terms are? False acceptance rate, that means it is accepting the sample, or it is allowing the person who is not authorized. So that is called false acceptance rate. It means sample is negative but it is treated as a positive. And false rejection rate, that means even the person is authorized, he is not allowed to enter. That means your sample is positive but classified as a negative. So that is called false rejection rate, something like that. Right? So equal error rate is the point where FAR and FRR are same. That is called equal error rate. At that particular point, both terms are identical, and it is computed as summation of these two divided by 2. This threshold is important in biometric system as it provides balance between security and convenience. If we keep equal error rate high, okay, then in that case the accuracy of model would be very high, fine, which is very critical in authorization in sensitive system. And ER can also be used as a benchmark to compare different security systems. So we have different algorithms, then we can see that what is the EER of all the different algorithms. The algorithm having high EER should be chosen for the security purpose, because it gives a proper balance at higher threshold. And if we minimize the ER, if we consider small algorithm with small ER, then that algorithm does not require a lot of training, lot of testing, or very high level of logic to have a good accuracy. But that algorithm would be simple, but in that case we are compromising the security, in short. So consider these are the true positive to false positive, etc. So FAR, false acceptance rate, is given by false negative, false acceptance rate. So we have accepted the samples which were not false. So it is given by false negative upon true negative plus false negative. So from this we can say that FAR is 0.24 and FRR for this is 0.32. So there is some variation. And so to compute the equal error rate, we have to add this 2 and divide it by 2. So equal error rate for this would be 0.24 divided by plus 0.32 divided by 2. So that will be approximately 0.27 or 8 maybe. Attack success rate. So as the name suggests, the term attack success rate usually describes how successfully cyber attack or security lapses are. So look at the formula and that would be clear that attack success rate is nothing but successful adversarial example, that how many examples have fooled the system divided by all adversarial examples. Right? So suppose we have 50 adversarial example and out of that 25 adversarial examples have fooled the system. That means the actual class was positive, but now it is being labeled as a negative. Fine, in 50 cases. So the ASR would be 50% in that case. Clear? So again, attack success rate is the ratio of the number of adversarial examples that have fooled the model on the total number of adversarial examples. And the last one is SSIM, Structural Similarity Index metric. So SSI model is based on the perception of the human. Okay, that how we perceive the image. So basically it depends on 3 parameters: luminance of the image, that is brightness; contrast of the image, that means how much intensity is spreaded over the image; and structure of the image. So the luminance of image X and Y is defined as 2 mu x mu y plus C1, mu x square plus mu y square plus C1. So mu x is the mean or the average intensity of the image X, mu y is the average intensity of image Y. Right? So and C1 is some constant. Contrast between these two images is given by 2 sigma x sigma y plus C2, sigma x square plus sigma y square plus C2, where sigma x and sigma y are the standard deviations of image X and Y. So we already know how to compute the standard deviation. And the structure of this structural similarity between these two image X and Y is defined as sigma xy plus C3 divided by sigma x plus sigma y plus C3. So sigma x and sigma y are the standard deviation and sigma xy is the covariance between image X and Y. Here C1, C2, C3 are the constant and they are added to avoid the division by 0. And SSIM or structural similarity between these two image X and Y is defined by multiplication of all these 3, LXY into CXY into SXY, and we can control the weightage of each by this alpha, beta and gamma parameter. So if we are more interested in weighting the luminance parameter, then we should have some higher alpha, etc. So doing this we can compute the SSIM between these two images. This is what the proto testing of proposed model. As you said, I have kept all 4 images. This is the original image. This is the attacked image. So we have added PGD, projected gradient descent attack, on this image and we generated this. Then this is the immune space projected image, and then this is the recovered image. Now this image size would look different. The reason is that image is going through so many convolution layers, and due to that sometimes there would be padding, fine, and then we are resizing the images, and that is why the image may not be perfectly matching with the original image size. But this is how we are reconstructing the image, and then we are doing the classification. Thank you.